Touchdown. You ever play that game? You ever play that game where you have to get it to... No? You have no idea what I'm talking about. Okay, while you're turning in your homework, we can get started here. Okay, so let's get started. Let's get started. Everyone ready? Ready to start? So the first part of your quiz this week is to write out what the meanings of the input and output quantities of sine and cosine are. All right, this is not just to give us something to do in the math class, something to memorize. The whole point of this is every problem that involves sine and cosine is making use. You should be making use of these meanings to help you solve the problem. Okay. So what goes into sine, what comes out of sine, you're writing equations, you're using equations, you're applying them to situations. So students who have a confident, immediate grasp of what's going into sine and what's coming out of sine can have great, quick, and efficient success on doing problems. That's the real reason I'm having you. We're pounding this drum, okay, of what is the input and what is the output. So without looking at your notes, let's practice. Okay, you all have to do it this week, and then we want to know this for solving problems. So the input into sine is what? Write it out. Take a minute. The output of sine is, see if you can do it perfectly the way you want to do it on the quiz. Okay, let's try the input into sine. Who can tell me what it is? Jenna.
The angle of swept counterclockwise from the 3 o'clock position.
The angle swept counterclockwise from the 3 o'clock position. So I'll be real nitpicky here. So that's good. But the angle is the object. What is the quantity related to an angle? So what do we call it? The quantity. The measure, right? So that is pretty nitpicky, but we do want to distinguish between angles as objects and their measure as the amount of openness. Okay. So, and then what unit do we measure the input into sine? It could be so it's kind of a trick question. It can be any unit. Okay. Any unit's okay. So the measure of the angle. Swept counterclockwise from the 3 o'clock position. That can be radians, degrees. We talked about gradients, or any angle measure is fine. Units. Okay, so you have to have all the details to get full credit. And again, it's not about just a memorizing exercise. It's about applying it to every problem that you do that relates to sine. What about the output of sine? Carlo, go. The y-coordinate, okay, which is?
The point on the circle from the amount of radius moved.
Okay, but what quantity is it? What quantity is it?
Radians from the horizontal axis.
Radians is openness.
Radius length.
Okay, it's the number of radius lengths. Dan.
It's basically it's sine theta is the distance above the vertical line.
The distance above the
Vertical line.
Horizontal.
Horizontal.
You did this, so you were thinking the right thing. So the distance is the vertical distance above the horizontal diameter measured in a fraction of the radius, or radius lengths. Okay, you could say radius lengths, that's fine. We're just emphasizing that that's usually a fraction of a radius length, because you get to a full radius length at the top of the circle. Everything on the way up is a fraction of that full radius length, and on the way down as well. Okay, so we got all the details. And then he said, what coordinate is that? Y coordinate. That's the Y coordinate. Okay, so then you'll do that for sine. Let's look at the quiz here. Tell me what?
Oh, no.
You okay? All right. So the first page of the quiz is doing that. It's the input and the output of cosine and sine, all the details, and what coordinate is it. Okay? And then the second half is filling out the unit circle. All the radian angle measures for the 16 key angles, right? For the radian angle measures, the degree angle measures, and then all the sines and cosines. So, what you should do is you should develop a system for generating it. Don't memorize it number by number, okay? You want a system for, I don't have it memorized number by number. I just have a way of being able to generate it every time. So I'll show you my way, and you can use that or make up your own. Okay, so the first thing is radian angle measures. We start with, of course, 0, and then we can start with splitting each quadrant up into 2 equal angles of openness. What angle splits up one quadrant into 2 equal angles in terms of openness?
30 and 60.
Okay, I heard 30 and 60 and 45. Now, first of all, I was asking for a radian angle measure. And I want to take a quadrant, and I want to split one quadrant up into 2 equal measures of openness.
5 over 3.
Whoa, guys. Wow. Better know this. Pi over 4. Pi over 4. Okay? So that is... So now you can just go to these points and count. All right, so we're going to just go every half quadrant. Every half quadrant, those are going to be pi over 4 at a time. So you just count. 1, 2, 3, 4, 5. Here we go, ready? 1, 2 pi over 4 is the same as? So 1, 2, 3. Again, this is not about copying down what I'm writing. It's about developing a system so you can generate it without having to memorize every single number on there. Okay? So 1, 2, 3, 4. What's 4 pi over 4? Pi. That agrees. We know that's half a circle. Okay? 5 pi over 4. 6 pi over 4 is the same as 7 pi over 4. 8 pi over 4 is the same as? So you just can split up each quadrant into 2 angles of equal openness and count. 1, 2, 3, 4, 5, 6, 7, 8. You're counting by pi over 4. Okay, now we're going to take a quadrant and split it up into 3 angles of equal openness. Each one of those will have how much openness in radians? Pi over 6. So we're splitting up. Pi over 2 is one quadrant, right? So we're split up into 3. So we're going to count by pi over 6s now. And we'll do this in red. So blue is the pi over 4, so we'll do red here. So pi over 6. And we're going to count 1. 2 pi over 6 is 3 pi over 6, does it agree? 4 pi over 6 is the same as? So 1, 2, 3, 4, 5. Yes, sir.
For the quiz, do we have to simplify it?
Yes, simplify all the fractions that can be simplified. That's right. So, yeah, 1, 2, 3, 4, 5, 6 pi over 6. Does it agree? Yes. 7. 8 pi over 6 is the same as? 9, 10, 11, 12. Okay, I'm not going to write them all down. Just showing you the system. Okay. So that gets you all your angles in radians. Do the same two things with degrees. What's half of the openness of one quadrant in degrees? 45. So count by, just keep adding 45s. Just keep adding 45s. 45. 90. Add 45. 135. Add 45. 180. Just keep adding 45. 225. 270. 315. 360. Of course, starting at 0. Okay, then we're going to do it again for degrees. We're going to break up one quadrant into 3 equal angles of openness. Which is what degrees? 30. So keep adding 30. 30, add 30, 60, 90, already got it. 120, 150, 180, already got it. 210, 240, 270, already got it. 300, 330, 360. So you just need to go around the circle twice. Adding 45 for every half quadrant, adding 30 for every third of a quadrant. And then we have the... And when you do this, whenever you have fractions, use the blank as the fraction bar, the way I did here. You see that? It makes it a lot easier to write. So for all these radian angle measures, use the blank as the fraction bar. And also for these coordinates, use the blank as the fraction bar. Okay, so at pi over 4, we use right triangles to figure out an exact value for what? The x-coordinate and the y-coordinate, or the horizontal distance as a fraction of the radius length, which was as an exact value? 2. And so because we're by symmetry, half of the quadrant, those were the same, and about, what? 0.7 of a radius length, right? About 0.7 of a radius length on that spot in the circle. And then we came over here, and I told you that at pi over 6, the y-coordinate, or the vertical position above the horizontal diameter, was a half of a radius length. And we figured out that the horizontal distance was, and that was about 0.87. Fraction, what fraction of the radius length is this point to the right of the vertical diameter, right? Exactly radical 3 over 2, about 0.87. And then for pi over 3, we have the same triangle, but now its legs are flipped. Now we're 1/2 of a radius length to the right, and up at this point right here, we're up above the horizontal diameter, radical 3 over 2, because it's the same triangle, just flip the legs. All the other sines and cosines of these 16 key angles then are, well, of course we have out here, how many radius lengths to the right are we? 1. How many radius lengths above are we?
0.
And how many radius lengths to the right are we? 0. How many radius lengths up are we? 1. Okay? All the other sines and cosines are just these same values applying the right positive or negative. So where, in what quadrants is the cosine negative? Cosine is negative. Is it negative in second?
Yeah.
Yes. Is it negative in third?
Yeah.
Is it negative in the fourth?
No.
Cosine's positive in the fourth. Okay? So cosine is negative. You're going to have all it, by symmetry, you're going to have all those same values, but they're opposites in the second and third quadrant for cosine. For sine, where's the sine? Less than 0. Quadrants 3 and 4, because we're talking about vertical distance above, so that's negative when you're below. So by symmetry, you're going to have these same values, like this is, this is the same distance above, and the same distance to the right, but now to the left, as this point. So at this point, its reference point is here. This one, its reference point is here. 2 pi over 3, its reference is pi over 3. Okay, what's the reference angle for 7 pi over 6? The quadrant 1 reference angle for 7 pi over 6. So what's the cosine of 7 pi over 6? What's the cosine of 7 pi over 6? Negative square root of 3 over 2. What's the reference angle for 300 degrees? So the reference angle will also always be the quadrant 1 angle that has the same magnitude of its coordinates. So the reference angle for 300 degrees is? Yeah, pi over 3, or 60 degrees. So what's the cosine of 300 degrees? I heard 1/2, I heard negative 1/2, and I heard square root of 3 over 2. So is it first of all, is it positive or negative? Positive, and the reference angle is 60. So it's going to have the same. It's 1/2. What's the other one we did? 4 pi over 3. Did I do sine of this one or sine of this one? What did I do before? I did the sine. I did cosine. All right, so negative. Okay, what's the reference angle for 7 pi over 4? Pi over 4. What's the sine of 7 pi over 4? Negative square root of 2 over 2, because we're below. It's going to have the same value, magnitude, as the y-coordinate for pi over 4. Okay, so this is a system to do it. You can develop your own system, but don't memorize it number for number. Okay, that's too hard. Okay, and then in a week you won't be able to do it at all, right? So if you generate a system, if you have a system for generating it, then in a year you can still do it. If you just know how to get started. Okay. So that's the quiz for this week in recitation. Is the key angles and their coordinates. This positive, just ignore that. I pulled this image from somewhere else and didn't black that out. So just positive, just ignore that. And then writing out the definitions of sine and cosine, the inputs and outputs. So just I posted current grades, four entries in the grade book. Your homework average, your quiz average, your exam average, and then your overall grade in the course as of, I think, Friday or Saturday. Okay? And then Blackboard has some entry called total. Is that right?
Yeah.
Just ignore that forever and ever. Just ignore that. I never look at that. Okay? So I do what I did with the 4 columns. I take all the numbers and I crunch them and I give you a grade. So I will never look at that total. Doesn't mean anything. But this is, so it was kind of disappointing, or I don't know what you want to say, but your homework and your quiz average was lower than the exam average. Okay, and so the point is, but the exam average was low. The point is that if you work hard on homework and quizzes, that can save a faltering exam grade a little bit. Okay, so take the homework and the quizzes seriously. I'm giving you guys the quizzes every week beforehand. There's no excuse that the average shouldn't be 85 or higher. But the average is like below 70 on the quizzes. So it's not good. So take it seriously. It's just going to the weather's just going to get nicer. So just decide that you're going to work hard now, okay? All right. But the whole point of the quizzes and the homework, not the whole point, but it's to keep you up to date, but then it's a way of kind of helping your grade if you're having trouble on the exams. which is a lot of you. So please take the homework and quizzes seriously. But then also that should help you keep on track and get you ready for the exams. Okay, so go to page 275 in your books. And read the setup. And then go right to number 4. So read the setup and go right to number 4. We got a circle today? Do you have a circle today? Page 275. And I want you to read the setup. So he's spinning a ball on a string, right? He's spinning a ball on a string. And what does it say? What's the details? It's a 2.3 foot string. He's spinning it around. I don't know why, but he's doing that. And he's turning it 3-point position. And then 4 says, let's get down to number 4, we say, suppose the ball travels 2 radians per second. 2 radians per second. So now you're going to work on number 4 there, where it's going. I'm showing about 2 radians per second. Yeah, that's pretty close. Okay, so they want you to write a formula for theta in terms of t, is that right? Is that one of your things you have to do? Okay, so that's pretty easy, and probably most of you could get that. But so here's a technique for writing a formula maybe when it's more difficult. So let's practice it on this thing. So to help you write a formula, a really helpful thing is to create a table of values. So for a given t, let's just generate, for different values of t, we're going to generate what the resulting values of theta would be. So when t is 0 seconds, what's theta? How much angle measure has been swept out? 0. Okay? After 1 second, if the ball is revolving at 2 radians per second, then after 1 second, 2. 2 radians of angle measure have been swept out. Okay? How about 2. How about 5? Okay, so then once you get enough values, you get to see the pattern of what's happening. So for every value of t, you get the corresponding theta. And so then you say, all right, let's continue the pattern and just say, what if t seconds went by? So how many theta of angle measure is swept out? How much angle measure is swept out given an amount of time? 2 times that amount. So that's our formula. Like I said, you might not need to do it for this one. Maybe many of you could just write that down. But when you have a situation where you're building a formula and it's a little more tricky or more complicated, it really helps to generate a table of values. And that helps you to deduce what the relationship is. Okay, so I'm going to put on this axis here that I'm showing you something about the ball spinning. Okay, and on this axis is theta, which is our standard angle measure of the angle swept counterclockwise in the 3 o'clock position. And so I want you to decide the output of this function. So this is our input. So what angle measure is that right there? Well, let's go back here. So what is happening here? When the angle measure is 0, look at what's happening. And we want to talk about what output is what quantity for the output is this graph showing. So what quantity of output is this graph showing? Everyone think to themselves. And then, given that, could you write a function we'll call it f? Could you write a function f of theta based on what output quantity this graph is showing? So let's see what you guys think. John, what do you think? What's the output quantity that this graph is showing relative to the ball?
Cosine.
What's that?
Cosine.
All right, but what quantity? So what quantity? So that's the function. He's suggesting cosine. What quantity is that? Like, what's the meaning of that? What about the ball is that showing? What about the ball is that showing? Not sure? Zach, what do you think? What about the ball is that graph showing?
Seconds, how far the ball's gone around radians.
How far it's gone around. So distance traveled of the ball? That's what that's showing. What do you think, Cameron? You with that? Distance traveled. Yeah? No, try again, Cameron. It's not distance traveled. What is it? Oh. John.
The distance above his hand.
The distance above his hand is a fraction of the radius length. That's what that graph is showing. Yes? Getting closer? No. Faisal, what is it? The horizontal distance to the right of the vertical diameter. How do we know that? No, not because it's cosine. No, cosine is the last thing we come to. Cosine is at the end, right? So we're talking about the quantity. How do we know, looking at that graph, that it's the horizontal distance to the right of the vertical diameter? Carlo.
It begins at 1, 0.
Right, and what does it do?
0 at the distance and the horizontal distance is 1.
Okay, so it begins, here's at the angle measure of 0, we have an output of some positive value, call it 1. And what happens, say, as the angle gets swept out? What does the graph do? Decreases to 0. Is that what the horizontal position of the ball does? Yeah, the horizontal position of the ball starts at 1 and in the first quarter circle decreases to 0. So that seems to agree. Then in the second quarter of a circle, the horizontal position goes from what to what? Kate wants 0 to -1. Agree? Yeah, 0 to -1. Is that what the graph does? Okay, so what angle is this right here? That's pi. This is the ball below the horizontal diameter, right? This is the ball below the horizontal diameter, right? No, this is the ball where? To the left of the vertical diameter. We're showing, so this is a little confusing because we're showing on this vertical axis of this graph horizontal position. So a negative value of the y-coordinate on this graph is talking about the horizontal position here at negative 1. Okay, and then in the third quadrant, the horizontal position goes from what to what? Negative 1 to 0. Does it agree with the graph? Going from negative 1 up to 0. Angle. That's our 1.5 pi, or 3 pi over 2. This was our pi over 2. Okay, so this graph is tracing out its output. The y-coordinate on this graph is tracing out the horizontal position of the ball. You should all be able to recognize that. If not before, now, from here on out. Because it starts at 1 radius length to the right, then it's at 0, then negative 1, then 0, then 1. So that's, and then we call that function what? That's called the cosine. Tracing out the horizontal position to the right of the vertical diameter is called cosine. I love it. Light bulb. Okay. So, is this all the angles that the ball sweeps out? 0 to 2 pi? No, why? What happens? What's that? Okay, but so this infinite number of angles from 0 to 2 pi, is that all the angles that it sweeps out? No, why not? You can go further, right? So it doesn't take long before we're starting the next circle again, right? So this thing's going around 2 radians per second, completes 1, does another rotation. So starting at 2 pi, I want to trace now, continue to trace the horizontal position of the ball to the right of the vertical diameter. Beyond 2 pi, what will the graph look like? That repeated. When will its repeat end? It's going to repeat what it started with until it gets to 4 pi. And then what's going to happen? It's going to repeat again. Okay, so this is called one cycle of output values. What we're seeing is, what I've shown you is one cycle of output values. As that angle continues to increase, we'll get another cycle that will start at 2 pi and end at what? John, what will it end at? So this second cycle will start at 2 pi and end at? John? 4 pi, right. Okay. So so what we're talking about, so we're saying that 2 pi is the interval of input values that results in one full cycle of output values. Would you agree with that? So there's a name for that. Anyone know it? What's that called? So the interval of input values, in this case 2 pi, that results in one full cycle of output values. Rotation. Okay, so it's one rotation of the ball.
Is it that period?
That's the period. That's the definition of the period. It's the interval of input values that results in one full cycle of output values. And so the period of cosine theta is 2 pi. So for different functions using cosine and sine, we're going to have different periods, but we're going to determine the period, always determine the period from this fact, knowing that cosine has a period of 2 pi. What about sine? Does it take a full rotation to repeat a cycle of output values for sine? Yes or no? Let's see. Here is sine. Maybe. There's sine, which tracks what quantity? Vertical distance above the horizontal diameter. What's the period of sine? What is the interval of input that gives one full cycle of output? Still 2 pi. Okay? So this is the key value we're going to use in order to find every other period of every other sine and cosine function. We're going to start always with 2 pi, knowing that their cosine has a period of 2 pi and sine has a period of 2 pi, allows us to then calculate other periods. Okay? And we'll see that in a second here. Question, please.
Will the period always be measured in radians?
Okay, let's just hold that. I think that what we do next will answer that question. So he's noting that this 2 pi is what unit? What unit of measure is that 2 pi? Radians, right? It's amount of openness of the angle. So he's asking, is it always going to be radians? So let's take a look. So now I want to do a new function. I'm doing it in blue. Called g. I want the same function, but now I want, according to the ball rotating at 2 radians per second, I want the input now to be time of this function, and then I want it to output the same horizontal distance from the right of the vertical diameter. So I want to write the input of this quantity g is going to be time elapsed since we started swinging, and then the output is going to be the horizontal distance to the right of the vertical diameter. Who can write what that function is? Can you tell me what that is? Freddie, any idea?
Sorry, what they did.
Okay. So we want the output of this function to be horizontal distance to the right of the vertical diameter. So what's the overall structure of this function going to be? It's going to give us horizontal distance to the right of the vertical diameter.
Sine.
Sine. Will be sine? Cecilia.
Is it 2 cosine?
2 cosine of t. All right, so overall structure, cosine. We agree with that? Is it cosine? Cosine. So, cosine of t? So, here we go. What goes into cosine? What's the input of cosine? Not time. What is the input? This is why we're memorizing it. Measure of the angle swept counterclockwise. And so what is that? Theta, which is 2t. Okay? We said theta equals 2t. What goes into cosine has to be theta. But now if our function is in terms of time, then we have to put in that 2t, which is our angle measure. Okay. Then we're going to multiply by 2. If the radius was 2 and we wanted it in inches, yes. Okay. Or whatever the unit is. But we're going to stick with just fraction of a radius here. So now, what did we say? The interval of input. So what is our input of the function g? No. No. The input into g is what? Time in seconds. Okay? Time in seconds is the input into g. And we want to find the interval of input, the interval of time. So we can do that by using the fact that the period of cosine is 2 pi. What does 2t represent? 2t represents angle measure, right? It's theta. So if we want one full rotation, we want 2t to reach what? 2 pi, you see? Because 2t is theta. So if we want to figure out what t will give us one full cycle of output, we want 2t to reach 2 pi, because we know that period of cosine is 2 pi. So what value of t makes 2t equal to 2 pi? Pi. So the period is pi. Okay, what are the units on that number? Is that radians, inches, seconds, something else? She wants seconds. Agree with that? Andrew, agree with that? Is that seconds, radians per second? Yeah, because what would we do? We solved for an amount of time. An amount of time that gave us an amount of angle of 2 pi, right? So it's seconds. So, Carlos' question. Is it always radians? No. Why? Because the period is the interval of input. So the input can be something different than an angle measure. In this case, the input is time. So it's going to be, the unit of the period will always be whatever the unit of the input is. Why? Because the period is the interval of input that results in a full cycle of output. So we can redraw the scale here for time, t, and what did we say one period in terms of t was? For g, the g function? What's our period? Pi seconds. Therefore, half a period is 5/2 seconds, quarter of a period, 5/4, 3/4 pi. Okay, so if we're looking at the g function, it's the same exact function of output, but now the input is what? One period is pi seconds instead of 2 pi radians. Okay, does it make sense? Okay, now I'm making up one, it's not in the book. So let's do something more realistic. So for a short string, this is impossible. Slinging it 2 radians per second, right? It would bunch up, right? The string would bunch up. So let's do something more realistic. We'll do 9.7 radians per second. That's not in the book. I made it up. Okay? That's realistic. So I want you to determine, so this will be red. So determine theta in terms of t. Write a function h that gives the horizontal position to the right of the vertical diameter as a function of t, and then the period of h. Find the period of h. Is the task clear? So for it's 9.7 radians per second. Write theta in terms of t. Write a function h of t that gives the horizontal distance to the right of the vertical diameter as fraction of the radius in terms of t, and then find the period of h. Compare with the person next to you. Well, think for yourself first. See if you can do it, and then. So, by the way, this 9.7 is called, the name of it is radial speed. Radians swept out per second, or per any time unit. Okay, did you write theta in terms of t? Jonathan? He wants 9.7 t. Agree with that? Yep, for every second that goes by, we sweep out 9.7 radians of angle, so you're going to multiply. Time times 9.7. Okay, who's got the function h of t? Dengi, did you get that?
Yes.
Tell me.
Cosine 9.7.
How do you do? Good, got it. So now we want to go through the process of finding the period of h. To find the period of h, we're going to say, we know that 9.7 t is what? That's the angle measure. And so to get one full period of cosine, the angle measure has to reach 2 pi. Does it make sense? We need that thing, which is measure the angle. When that reaches 2, we want the time for that to reach 2 pi, because that's the angle measure. So we get 2 pi over 9.7. Let's get a decimal approximation, because you wouldn't say, oh, he's swinging that ball, and it takes 2 pi over 9.7 seconds. 9.7 to whatever, right? You're going to say instead 0. Is it 7 or 8? 648. Okay, units on the period in this function. Seconds. Okay, so let's change the axis again for this h function. All right, our period is. So one thing you'll need to do, we're going to start in a little while. We're going to be next week graphing some more complicated sine and cosine functions. One technique that you have to have is find the period and then break it up into 4 parts, 4 equal amounts of time, and find those times. Okay, so for a period of 0.648 seconds, can you find what these 4 time values are? There's different ways to do it. You just have to have your own way that's most comfortable. So we're going to split up the period into 4 equal time periods to help us sketch graphs eventually. So practice here. Get those 3 values of time that break up this period into 4 equal time periods. Go. Do it. Do it however you want to do it. Here's one way. You start with 0.648, divide by 2, and that will give you the half period. I think that is 324. Is that right? Then take that number to get a quarter period, divide by 2 again. This is another way. So this is 0.162. And then there's more than one way to find this. You could take 3/4 of that. Or you could add these 2 together as long as they're good approximations. And what do we get for that? 486. So however you can do it, but you'll need to be able to do that. Right? Given a period for one full cycle of output, split that up and get the values that split it up into 4 equal quarter periods. Okay. Questions about this example? All right, so let's summarize here. Can I erase? Any questions? So our f function. Next slide. Okay, so we started with the f function. We said f was cosine theta, I think, yeah, right. And so the input of this function f is theta, which is measure the angle, so counterclockwise from 3 o'clock position. Then we switched and we looked at this h function, which was a function of t. The input of h is t. But we saw that this thing right here was very important for us for determining the period. Okay, so we have a special name for that so that we can distinguish between the input and this whole thing that's going into cosine. All right, so we call that the argument. Okay, we call that the argument. Doesn't mean we're mad at each other. Okay, it's just the name for this entire expression that's going into cosine. All right, and so if we're paying attention, what quantity does the argument represent? What quantity will the argument of cosine represent?
I
Okay, he wants angle measure. Agree with that? So this is one reason why we've been working on input and output of cosine and sine, because what the argument is, what it represents is, in a sense, it's the input into cosine. And we know the input into cosine is angle measure, right? Measure the angle, so counterclockwise from 3 o'clock. Okay, but now in this function we have this other, it's not, the angle measure is not the input. The input is time. So we have both things that we got to keep track of, right? So we have input of the function, and now we have the argument of cosine, which is what we called the input of cosine before. So it's the input into cosine, so it's the measure of the angle, so counterclockwise from 3 o'clock. All right? What is the meaning of the period? Can you write it without looking, without peeking at your notes? Can you write out the meaning of the period of this function? See if you can do it.
Function's missing a C.
Thank you. Okay? So, does it relate to the input or the argument? The period. Directly. Does it relate directly to the input? Is it something about the input or something about the argument? The period. I heard both. What is period? Period is the interval of input. It's the interval of input that gives us a full cycle of output values. So in this case, the unit was what? What was the unit on the period? Seconds, because the input value was time in seconds. Time in seconds since we started twirling. Now, to find that value, we use the argument. But the period itself is directly related to the input. It's the interval of input that gives us a full cycle of output. Make sense? Okay, let's practice. Here's a I gotta do something first here. I do this. Mute, projector mute. Beautiful, okay. So I have a very good exercise to practice all this. I just have to reset the answers here. Okay. Excellent. Okay, a large Ferris wheel is rotating counterclockwise. The associated units are meters, radians, and minutes. A function related to a car on this Ferris wheel starting at the 3 o'clock position is this. F of t equals 28 cosine 3t. So this is a really good exercise. I've taken that rule of that function and I've split it into every possible sub-expression that there is. T, 3t, 3, cosine of 3t, 28, and then the whole thing, 28 cosine 3t. Every one of those would generate a value for a given value of t, okay? You're writing out the meaning of that value, okay? You're writing out in sentences, like a sentence, that describes the quantity that expression represents. Okay, so answers are not like input, argument. Those aren't the kinds of answers I'm looking for. I'm looking for, the temperature in the room since 3 o'clock. The distance from me to the chair, whatever, like that. So you're writing out quantities. What quantities related to the scenario do these expressions represent? Okay? So then this isn't just a piece of cake. You have to think about it. Okay, but it's really. I want to know what you look for 3t. Are we getting this? Did you get 3t? Thanks. Good. 3t.
Okay, which one? Measured in minutes. Fraction of a radius. Cosine always outputs fraction of the radius or radius of the 3t. 3t. Good. You guys are doing it. What quantity is 3t? Angle measure, right? Angle measure.
So what is
What is 3t? Sean, did you get what 3t was?
Yeah, it's the
In what?
radius.
Yeah, so you really, oh yeah, so meters, radians, and minutes, right? Okay, so yes, you could know that. Okay, 3t, because it's going into cosine, and last week we got this. Because it's going into cosine, it's going to have to be measure the angle. What does just the number 3 mean? What is just the number 3? Right, so it's the radial speed of the wheel. In radians per minute. If t is minutes and 3t is radians, then 3 has to be radians per minute to make that work, okay? To get that to work. And we saw that before with the radians per second. We saw 2 radians per second made an argument angle theta of 2t. And 9.7 radians per second made an argument of also of 9.7t. Okay, cosine of 3t. Let's have someone chime in here. Aaron, go.
It's the horizontal to the right of that
In what? Here's the key. In what?
fraction of the
Good. This is just straight up cosine. Straight up cosine will always output a fraction of a radius. A number between what and what? What's the minimum and maximum that cosine will give? -1, all the way on the left side of the circle. That's the greatest fraction of a radius we could have, a full radius to the left. And the greatest value of cosine we can have is +1, a full radius to the right. If you're on the circle, you can't get any more than 1 radius away from the center if you're on the circle, right? So the most it'll be is 1, least -1. Okay, the 28 in this context, what will the 28 be? Yeah, Kate.
The radius of the Ferris wheel in meters.
She wants the radius of the Ferris wheel in meters. Zach likes it. Okay, finally. 28 cosine 3t. Dan, did you get this one?
Yeah, that's the coordinates of where the well, specifically that's meters where it's on the circle.
What quantity is it? So think quantity. Think temperature, volume, speed, distance. What is it?
It's radius, meters.
What is it? Those are units. What quantity is this? What kind of quantity does this give? Does it give a speed? Does it give a distance? Does it give a temperature? Does it give a volume? A distance. Okay, what distance does it give?
It's the distance from the original 3 o'clock starting position to where the meter is currently.
That sounds like you're measuring distance traveled. It's not distance traveled. How about Fahia? What is this?
Horizontal distance rather than vertical diameter in meters.
Now in meters. Why? Because our radius length is 28 meters, and this cosine, this is beautiful. Look at this cosine is going to give us the right fraction of 28 meter radius. So it'll give us our horizontal distance in meters, because this will be the fraction of 28, and we multiply. Right? We're going to get that fraction of 28 will give us the horizontal position at any given moment of time. What's the input? Which one of those above is the input? T. What's the output? Which one? Cosine 3t? The last one is the output. 28 cosine 3t is the output. And what's the argument? 3t. Okay? The value of the period. So to get the value of the period, we know that cosine has a period of what? 2 pi. So we want the argument, that expression of the argument, or the angle measure to reach what? 2 pi. So when 3t, which is the angle, reaches 2 pi, we'll have a full cycle of output values. Do you see it? That's an important kind of reasoning to have. You got to have that reasoning. That, all right, the cosine, when that thing reaches 2 pi, we'll have a full cycle. So I'm going to take 3t and make it 2 pi. So therefore the period is 2 pi over 3. Let's get a decimal approximation. 2.09. Let's just say with that. Units? Radians? Seconds? And 2.09 minutes is the what? This is the period. And what is that? That is the... Okay, it ends up being right. The time for one rotation. Because what? It's the interval of input that results in one full cycle of output. Right? The interval of input that results in one full cycle of output. Okay, so we got all this info, and we can sketch it ourselves. No technology. Here we go. So we start with a full period. We said was what? 2.09. So here is from 0. I don't know if you can read that, but so this is 2. This is 1. This is 3. Okay? And this is 10. This is 20. This is 30. Okay, so we got our period was 2.09. And what do we got to do? So to sketch this now, so that's why we did this before, and we'll be doing it a lot. We need to get 4 equal time periods that are each a quarter of a period, and we need to get those amounts of time from 0. Okay? So we can start by taking half of a period, which is just going to be a little bit greater than 1. 1.045. Okay? And then to get a quarter of the period, do that. Take a quarter of that or take half of that, which will be just over 0.5. 0.5225. And then you got a couple different choices. How are we going to get this amount of time here? You can add these two, or you can take 3/4 of that. And what do you get? 675? Okay, so we broke up one period into 4 equal time quarter periods, because that's how the structure of the graph looks. And then we want the, at a time of 0, what will the horizontal position above or to the right of the vertical diameter be? In meters, at 0. 28, we know it's at 0 at the 3 o'clock position will be at 28. And then a quarter of a period later, where will we be? Top of the circle, 0. Okay? And then the next quarter cycle, the horizontal position will go from 0 to what? Negative 28. Next quarter cycle from negative 20. So here we are at the bottom of the circle, right? Right? Bottom of the circle. Yeah? Yeah? No. What side of the circle is this? Left side of the circle. We're 1 radius length, or 28 meters to the left. Okay? So then in the third quadrant, we go from negative 28 to, and now we're at the circle. Bottom of the circle. Last quadrant, we go from the bottom of the circle to 28. All right, wait, see if it's right. It's the best part. Turn on the graph. Nailed it.